things properly. They are not doing things up to request. So there's really a difference there. Sorry? I mean like it's not like follow exactly, but then the main thing is not in there. Sure. I mean, my point is the main thing is not in there. So sometimes a bit frustrated, but then there's a learning process. Okay. So let's continue with P groups. Anyone still remember what's the definition of P group is? Power of prime, power of positive power of primes. Okay, yeah, positive power of primes. Yeah. And negative sounds a bit scary. Yeah. Okay. So we proved that the center of a P group is not trivial. Okay, using class equation last time. So now maybe we can show something extra here. So let's say we have a group of order P squared, then it should be abelian. Okay, for example, 9, what else? 4, 4, I think 4, you know what kind of group you have, right? The Klein 4 group, and then the C4 cyclic group. Both of them are abelian. Yeah. And then, sure. Okay, so let's prove this. So this proof actually is very simple. Very simple. So, so we know that by previous proposition, its center is not trivial. So maybe say its center Z is not trivial. Okay, so what could it be? So the order must divide the order of the group, right? Center from a subgroup in particular. So the order of Z must be either P or P squared. Okay, so if it is P squared, then we are done basically. So we need to like rule out the possibility of P. Well, okay, so let's suppose the order of Z is P. Okay. Then meaning what? Meaning there are something in the group G. Okay, let's call this group G lah. This group G, X means G, such that X is not in Z. Okay, then you can actually consider the centralizer of this X here. So in particular, this centralizer should contain X. Okay, maybe I'll write it this way. At the same time, this centralizer should contain Z. Okay. So note that I use contains for two type of things here. One is element, one is subset. So be careful. Okay. Yeah. This is some mistake that other grade will make as well because they heard their teacher say contain. They also contain. No? They don't know what is the element or what's the subset. But then be careful. When we talk about elements or we talk about subset. Okay. Actually what? Actually this centralizer, I can say that it is strictly greater than Z, strictly larger than Z. You know why? Yes, because X is not in the center. And then X obviously commute with X itself. Okay, so obviously X equals to XX. Okay, so X is in ZX. Right? Why? Obviously, I want to do that, so why? Yeah. The only number that's greater than P and then that divide. that can divide p squared is p squared. Yeah. Okay. So since the order of zx divide the order of g, so it must be equals to, and at the same time, the order of zx is strictly greater than the order of z, which is p. So the order of zx must be p squared. Does it make sense? 啊，就这样吧。Yeah, very simple. Algebraic proof is like this, right? It's group theory. Yeah. Okay. Does it make sense? Yeah. So if p squared were 9, if it's not, if it's p, but we deduce that it's actually have to be p squared. The centralized elements. So okay, so if it is so therefore zx is equals to g. So meaning what? Actually, that is at x actually commutes with every element in G. So it turns out it is actually in the center. Okay. So we're done. That is x in Z. Okay, good. Any question? Question? No. Okay. Then in this case, a corollary is a group of order p square is either cyclic or the product of two cyclic groups of order p. Okay, how to prove this? Huh? So if you have a group element that's of order p squared, then you can use that to generate a group, the cyclic group. If not, then what? Then that means your group element must have maximum order p. It can't be the case that everyone is order 1, right? The case. Oh. What? Yeah, that's right. That's right. Yes, that's right. Okay. So then then if not, okay. So okay, maybe let me write down what I say. So if G contains an element A such that, okay, I think in this class you guys use this notation, right? Let's use this notation. What? Yes. Yes, but in master we free a bit. Okay, we use this notation. So then G can be generated by this element. If not, then every element of G that different from identity should has order P. So then how do you form this group then? Then you just take any xy in G such that their order is P. And definitely you can find this Y not in the subgroup of X. Otherwise, you don't have so many P square element there. So then by a proposition, there's a proposition on product groups, which is very important. I think none of you mentioned it last time. Did anyone mention about universal property of product group last week or the week before? Sorry? Oh, sorry, why is not in it? So product group property here is as long as you find two subgroup, which is normal, and then their intersection is identity, then you can find this isomorphism. I think it's in my notes. You can go and find it in the product group section. Basically, I think if I can recall, I think you need this 2 be equal to G, and then the intersection is empty. No, not empty, but just identity. Anything else? I think I can remember this one. Then, huh? Oh yeah, normal stuff, right? So which one is normal? One of them, right? I think one of them is normal. In our case, it's normal, right? Because we proved that. Did we prove? Oh no. Order P group is always abelian, so it's normal. And so this one implies that G is isomorphic to the product of these two subgroups. I think or here, either one of them. Later we will have an upgrade version of this. Instead of direct product here, we can consider something called a semi-direct product. Yes. Okay. So there's a non-trivial multiplication here. Here is just the normal one. It's just I cannot say this is a multiplication, right? This is just a product group. So this is a tuple. But then how we view this isomorphism is by group multiplication. So maybe I can write down this isomorphism for you, but then you need to verify that. So let's say here is x1. And then the map here is just x1 times y1. This is the isomorphism. Hence the sentence here. The sentence here is the product in the group. You can get everything like this. OK， 有问题吗？ simple。这个 order 是不是 p square？ 这个、这个这边 p 吗？这边 p 吗 ？p 乘 p 不是 p square 的。对呀、对 ，isn't it right？ 所以有个 p things here，p things here，p times p。喂，不是你现在问我的问题是这个人的这个的 order 是什么啊？你问我的是okay. So you are asking me. Let's say I just take this generator and then I consider this element here. What's the order of this element? Okay. 这个 order element 是 P， 这个 order 是 P 啊。So who is the order P square? Are you asking? Right. Which one? Which element can give you order P square? Wait, no. Wait, don't confuse. So the order of a group is just say how many things there. It doesn't tells you that every element there have to have order P square. Right. Because in particular, this one we already assume that there's no order P square already. No P square. Yeah. So you cannot get order P square element from this product. No. Cannot get. If you have, then your group is a cyclic group already. Okay, good. 221. Okay. In that case, before we go into Sylow theorem, maybe quickly go through this Sylow theorem. Let's quickly go through this normalizer stuff. So if you have a conjugate action, right, you can define a normalizer of a subgroup. As normalizer of subgroup. So meaning these are the G such that GHG inverse is X. So this is action on subgroup. Okay, just previously we have the conjugate C class and what? Centralizer, right? Those are the action on the G, on the element of G. But then this is action on the set of subgroup. Understand what I said? Previously here is element and now is a subgroup. So it's a set of subgroup. So you see how this G sends the subgroup. to which subgroup it sends. So if it sends back to H, then we'll call this normalizer. So this is a bit like the centralizer, right? Centralizer is just replacing the subgroup as a element. So there we call centralizer because it's center. But now, if you are like conjugating a subgroup is a normalizer, you need to think about what's the definition of normal subgroup. So this is definition of normal. Things that make this actually normal. So normal when H is normal, right? NH should be G. When H is normal, NH should be G because normal subgroup is what's the definition of normal subgroup? For every G, GHG equals H. So this is a bit like the central and centralizer, the concept between central and central. Sorry? Yes. Yes. It is a group action on set of subgroup. Yes. Yes, that's right. Yep. Yep. These are group properties, so we can jump. Maybe you jump. These are properties. Let's see. Anything worth to mention here? I think C follows from A and B because they are subgroup of N and then wait and see. So N is a subgroup of G. I think you can show it directly, and then H is a subgroup of N by A. H is a normal subgroup of N. You know what it means? Huh? What it means?
I mean，拿 n 二你去取了所有句子线，
Yeah.
conjugate 是等于自己，所以 h 在 n 里面就是 normal。
Yeah. Yeah. So basically, when we say H is a normal subgroup of N, then you need to check for all elements N and H, and inverse is H. This is what I told you just now. If H is normal, then everything will conjugate with H, sending back to H. So the normalizer is G. Okay, by definition. You guys know the definition of normal subgroup? I think no one presents this. You present normal? Or because you need to speak about concept, is it? Yeah, normal subgroup. Okay, very important. Oh yeah, right. You mentioned about the left-right concept, right? As you go back and check, right? Is the same G you use, right? I remember. Okay. Yeah, good. Okay, any questions so far about normalizer? I think the most important definition is this one. Maybe I will be with this one. Sylow theorem. Sylow theorem? Sylow theorem. So let's start with Sylow theorem. The purpose of Sylow theorem is also due to classification. So we want to classify certain groups. Maybe we want to classify all the groups, but then it's kind of tough. Okay. Well, so let G be a group of order n, and let P, so let prime P divides n. Okay. So you could imagine that you can put out a few P, right? Depends what number you had. But then let's take the largest power of P. Okay, let's take the largest power of P that divides n. You could do this due to the fundamental theorem of arithmetic. Is it white code? Yeah. Okay. So that n equals to P to the E times M. In that case, then this M here shouldn't divide P lah. Okay, otherwise you can pull the P out again. Oh, sorry, the other way around. P cannot divide M. Right. So then there's a so so then the subgroup of G of order maximum power of P is what we call a Sylow P subgroup. Sylow, Sylow, Sylow P sub. Okay, need to be the maximum power largest. Right, so far okay? So far okay? Uh, should this subgroup always exist? What do you think? Why? Huh? Name. That's right. Yeah, so this question is very natural, right? I mean, like, um, so Lagrange's theorem says what? Lagrange just tells you that the order of the subgroup must divide the order of the group. It doesn't tell you that if your number can divide the order of group, must the subgroup exist or not. It didn't say it that way. Okay. So, the first thing that the Sylow have is every. Okay, maybe let's jot it down. So this is the first Sylow theorem. So it's non-trivial actually. A finite group whose order is divisible by a prime P actually contains a Sylow P sub. Okay, so meaning if you have finite group, you look at the group order, whatever prime you found in the decomposition, you can find a Sylow P subgroup. So you might think of how I'm gonna find the generator. What do you think? You have any idea how on earth you're gonna find this subgroup? Okay, kind of tricky, very tricky here. Maybe let's look at the proof. So it's a very tricky proof here. I'm not sure how they found out this proof. Maybe they are looking at something else, I think. Something else, which is the thing I'm going to show you now. Yeah. Otherwise, it's kind of hard. How are you going to, like, in general, how are you going to find this parameter? Okay. So what they do is instead, you look at all subset, okay? Just subset, subset of G of order P to the E. Okay, the maximum one, maximum E that exists. What's the tricky part is how we're gonna find the subgroup. Very genius way. So we're gonna show that one of the subgroup or subset, not subgroup yet. One of the subset, let's say U, let's call it U. Is it necessary to call it U here? Okay, let's call it U of order PE actually has a stabilizer of order P to E. Okay, so meaning I look at the conjugate action of G on this order PE subset here. And then we show that the stabilizer of one of the subset has order PE. Then stabilizer will be obviously a subgroup already. Okay. So to find this subgroup, we go and find stabilizer of the conjugate action. Does it make sense? Oh, it's really Okay. Does it make sense? Okay, to find this PO subgroup, Sylow subgroup, we find the stabilizer of the conjugate action. So far, so good. It's not clear that how to find out, but then is it clear that after we found the stabilizer, it is a subgroup? Is the P Sylow P subgroup because the order is the maximum. Oh. Okay, so how to find this? Well, how to find this? I think how should I present it to you? sorry, sorry, not conjugate action here. It's just the normal one. So let me tell you what's this stabilizer for. So this action, I didn't tell you two lemma, but I'm gonna tell you later. But then this stabilizer actually is the left multiplication action. It's not the conjugation, it's just the normal left multiplication. Mm. Oh, 也是觉得热。Don't you guys feel warm? Yeah. No, you okay? Okay. I'm very hot. Don't just warm. Okay. Right. So what should we do next? Okay. Maybe we should mention a bit of this left multiplication action before we continue. Let's mention a little bit of these some property on this left multiplication action. Okay. So first property is if you have a subset of a group G, okay, so maybe here I put a group. So maybe here, just a subset of a G group, a group. Can I write like this? Is this a proper English? So if I put in front here, also very funny, right? Okay, let me put at the back. Why? You want me to write in English? Yeah, maybe write like the short form, shorthand, shorthand. Let this be a subset of G. G is a group. Okay. So then we can talk about the order. Okay, the order of the stabilizer. Okay, maybe let's try like this. Then the order of the step U. Okay, will divide U and G. The order of U and G. For left multiplication by G. Okay, I think this proof is relatively straightforward, right? Why is it relatively straightforward? Huh? Yeah. Yes. Both. Well, to divide to divide G, it just says that this is a subgroup, right? Subgroup is fine. But why divide U? The order of U. Why divide the order of U? What can you do from a subgroup to a group, to a set, a group action? Okay, right? The one you presented, you should know. Subgroup coset partition, what's the relation? Huh? Oh yeah, class equation, yeah, sure. I mean like yeah, cool. Yeah, right. So I mean yeah, that one is true, but then yes, yeah, I think related to class equation, yeah. But then what's the main point here? your set should be partitioned into coset, right? Okay, your set should be partitioned into coset. And so what's the coset we are looking at? Right. So I got that. Step U actually partitions U into orbits. Maybe let's call this step U orbit. Left or right coset? Is it a left or right coset? Hmm? Ah, 什么？ Yeah, the claim here is these are right coset. Hmm. Oh, does this make sense? Yes. Oh, what's the definition of step U? Stabilizer. So, okay. Okay, so I think we need to recall what step means. Yeah, so stabilizer under conjugation is this. Oh, okay. So we just talked about conjugation stabilizer, huh? So in general, what is the stabilizer definition of stabilizer? So basically, it's like G dot X equals to X. Yeah, dot X equals to X. But then just now we are looking at a subset, right? So that's mean you need to have oh, we have a stabilizer of a set. So I guess let me think first. Should I let it equal at every element, or can I just go back to this U is enough? Let me think. Let me think first. So, set of subset. Okay, good. So I think we are confused with one thing. Maybe I'm confused with one thing. So okay. So here the action here is a left multiplication action on actually is on set of subsets. Okay, then this one make more sense already. Okay, so meaning this action here should be, so let's write down the definition of the step. So step U should be, or the G in G such that GU equals to U. Like that. Yes, is the whole set. Yes. Yes. Action on the subset. Action on subset. Get what I say? You get what I mean? Okay. Yeah. Yeah. Okay. Cool. Very good. Mm. So does this answer why is it a right concept? Let's pull it up.
That's the
Partition 我的 U， partition U。U 一定在 U 里面有想象。What do you mean by that? Set U
就是 step U partition 就是 step U app 在上面有它 orbit partition U。
啊，对。
所以是 step U dot
Step U dot U obviously 一定跑进去 U 嘛。对，没有错。But then now we want to think about as a partition.
Step U dot U。那你对就变成一个 partition 它 it's yeah 是 right
啊？
是 right。
是 right cosine 啊？为什么？
相当于是的，后边的是 step U 里的东西乘了 U。
我的 orbit 我想看。
So one of U is orbit is everything
in step
times U.
对，没有错。
So U 的 orbit 就是 step U。
Okay. Okay. One way to think about it is this part here. This GU equals to U is very tricky. This GU equals to U is what? You are not sending UI to UI. You can send UI to somewhere else. It could be permutation. Okay. It could be permutation.
这样就 orbit 咯。
啊？
这样就对啦。
这样就有 orbit。再给我想象一下什么？I think something confused me is like why isn't it just U?
That's the one.
Just U.
I'm just
The thing. Let's call that maybe just one constant. Why do you have partition?
because of the orbit is making the action may not be transitive.
The action may not be transitive. Anything. The may not be transitive. You mean step U might not be transitive. The action of step U.
So you can have more than one.
I think makes sense. I think makes sense. Should we draw this? Can we draw this? Examples? Do you have examples? I can't think of any example for now. But I can what kind of my exercise? MA1 start giving me exercise, you know. Does that prove that I simplify already? Prove that there's no integer between 0 and 1. I'm gonna prove to them this thing. Okay, but never mind. Okay, so I think it's a good point here. So step U might not be transitive. Okay, so meaning although you preserve U, right? But then the way you obtain all the U is different. You get what I say? Am I saying the right thing? That's a good question. Okay, 想想看。也是你的 G。
Step U 只是确保说你不会跑出去，但是在这个里面的话，它不一定是跑为全部的。
因为应该
对，我想要写出来，我想要画出来，我想画，你画画看 ，OK。我本来是想要 like maybe there's 3-4 things here 啦 ，right？ And then maybe your step got G1, G2, right？ 画讲好来。
就比方说，我这边这里面有6个点。它可能就这个区，这个区，这个区，这个，然后这个区，这个区，这个区，这个。
哦呀，是。works. Okay, works. Does it make sense or not? 懂什么意思 ？So let's say these dots are the UI, and these arrow are the G action, right? The step G action. Okay. Although it sends all the point back to the point in the set, but then you can see that there's a partition. Like the orbit, there's only 2 orbit here. Right? Does it make sense? Okay. This is a very important concept, I guess. Yeah, very important concept. Yeah. Yeah. 就是什么？Yeah, sure, definitely. Yeah. Alright. Okay. So this part is like this. And then there's another lemma. Okay. So let n equals to p to the e to the m, such that e equals 0, and then p doesn't divide m. Then the number n of subset of order p to the e in a set of order n is not divisible by p. Okay, so meaning if you consider all the possible p to the e order set, right, subset, this total number here cannot be divisible by p. Okay, very the number, sorry, the number n. The number n of subset. So if you look at this collection, okay, collection of order e p to the e subset, then this set cannot be divisible by p.
如果 divisible 的还有就 p 加一乘。
If it's divisible, then what happens?
就是多一个 p。那你的还有是不是一样？
是这样讲吗？No, it just no. This number is just the cardinality of subset of order p to e. Yeah. Not subgroup, subset.
这我有觉得以后两个问题真的。
应该不可能，应该不可能，不可能，应该不可能。不太可能，因为这个是个 random random 这是 random subset，我把 e 拿掉，我把 identity 给它抽掉就可以了，对不对 ？I remove the identity from this subset, then surely this cannot be a subgroup. This is just random. This is a combinatorics thing. Yeah, this is a combinatorics thing. So, well, I think this is a combinatorics argument here. So, if you do n choose p to the e, right? This formula looks something like this. P to the e times p to the e minus 1, and then p to the e minus k. Okay. P to the e. P to the e. Oh, yeah, sorry. P to the e. So, well, the point here is, okay, what's the point here? The point here is if e divides p to the e m minus k, which is the term above here because n equals to p to the e m here. If and only if p will divide p to the e minus k. Okay, so if you divide the top, must divide the bottom. So that's why they can cancel out all the p factor. Does this make sense? I think if p divides this term here, then p should divide k, right? So you can do a p factor. But then if p can divide k, surely p divide this. But then the other case is it's the same thing. It's the same argument. It's just an extra m. That m is not divisible by p. So okay, good. Okay, so these are the two things happens here. So so from what we know from that two lemma, what do we know? So the cardinality of this x here is n, okay, which is not divisible by p. So well, how should we express this n here? With previous lemma. the cardinality of this x here is n. And then at the same time, we know the class equation, right? We can write it in terms of orbit. But then we know that P doesn't divide this guy, this n here. So what does this mean? So at least one of the orbit has order that is not divisible by P. Okay, so at least one orbit has an order not divisible by P. Okay, make sense? Okay, at least one of them is not divisible. So say the orbit. So say it is the orbit of the subset U. Okay. But at the same times, okay, you also know that sorry, say again. So this one is class equation. Is it class equation? Oh no, class equation is just for conjugation, right? This one is just conjugacy class. I mean, not conjugacy class, but then 对，就是 orbit partition. Okay, 就是 orbit partition.
Space.
对。Okay, so a step of U should divide the order of U. But then do we know the order of U? We set it as P to the E, right? This is how we pick the subset. So what does this mean? What number can divide P to the E? 1, P, P to 2, P to 3, up to P to E. So step U is equals to P to the M for some M. But then, what do we know? The order of step U, orbit stabilizer theorem, right? I think presented by Yu Han. So if you multiply with the orbit, order of orbit, you should get your order of group, which is P to the E to the times. But then we know that P doesn't divide order of the orbit. Therefore, composition here. Sense. Sorry? Ym is greater than 0. Let me think. Or maybe greater or equal. Greater or equal. It's just a power of P. Okay. So therefore, so what's the decomposition? You have, so O to the U doesn't have prime P factor. So all the prime P factor should go to the step U. Okay, and then the order of the orbit is just okay. So step U is the desired Sylow result. Okay. So here what we use is the Lagrange theorem actually. Okay, applying to the group action. So combine the Lagrange theorem and group action. But then there's some combinatorics result that you need to know. I think that's it. Okay. Any question? Kind of tricky. Yeah. The question? No? Okay. Okay, can follow. Okay, since we prove this, then maybe the next few one I leave it for you to figure out yourself. Maybe we just introduce it. So second, maybe let's introduce all of them, then we can take a break from here. Right, so the corollary is a finite group whose order is divisible by a prime P contains an element of order P. This is Sylow 没有就有了。Yeah, I think it's one of our tutorial or assignment problem, right? Or cheating, okay, good. Yep. Okay. So meaning this Sylow P group actually is redundant and you just yeah, depends on yeah. Okay, good. Yeah, okay, never mind. Then the second Sylow theorem is if your G is a finite group of order divisible by a prime P, then the Sylow P subgroup are conjugate subgroup. Okay, this one is very interesting. It means that no matter what Sylow P subgroup you found, they are actually just conjugate to each other. They're just conjugate to each other. And then every subgroup of G that is a P group, it will contain in a Sylow P subgroup. So this Sylow P subgroup is kind of a mother P group. Okay, so if you have any other P group, right, it should contain in some Sylow P group. Because Sylow is the largest P to the E, order P to E. Okay. It makes sense to think about that, and then it actually turns out to be true. And a conjugate subgroup of Sylow P subgroup will be a Sylow P subgroup too. What does this mean? I think it's just a converse of A. Trivial, yeah. If you have A, I think this sentence will come up. Oh, you mean how to prove A? The last one? I mean, isn't it? And then, yeah. Yes. Exactly how you prove A as well. Exactly how you prove A as well. Yeah. Is it? No way. Don't think so. A is a similar difficulty as the last one. You mean you start with a Sylow P subgroup, right? Then you try to conjugate it. Usually it's a Sylow P subgroup. I think it's
So if you have two series of P subgroups, you need to prove that they are conjugate.
Yeah.
Oh, that's what you meant. Let me see. So what they did here. Every pair works. So okay. So I think they start with B first. In the textbook, they start with B first. What they do is they show that some conjugate subgroup of H will contains K. So what's K? So maybe I show you what they did. But we don't go into detail. So they start with proving B first. So they start with a P P group, P subgroup, P groups. And so maybe just P group, no P subgroup. So I'll start with a P group. And then you start with Sylow P subgroup H. Then we will show that some conjugate of subgroup H prime of H contains K. Okay. So might not be the H will contains K, but some conjugate of it must contains K. Makes sense? Okay, so you look at the question B here, it contains in a Sylow P subgroup. So it might not contain in the one you started with, but after you conjugate cleverly, then you answer the contents. From there, you can prove A, why? Because your K and your Sylow subgroup have the same cardinality, like what it says. And they should be the same group. Because B is just containment, right? For A, you have equality once you have the same cardinality. Okay, good. Okay, so detail I left it for you. So corollary is a group G has just one Sylow P subgroup if and only if that subgroup is normal. Okay, because the conjugate subgroup will turn out to be the same one. So this gives another criteria to check whether a subgroup is normal or not. I think a Sylow P subgroup to be normal, not every subgroup. It's just a Sylow P sub to be normal. Okay. So meaning every other conjugate Sylow P subgroup come from the same subgroup. And then the third one is so let X be not the number of Sylow P subgroup. So you might have more than one, or if there's one, then your subgroup is normal. If not normal, then you have more than one. Then this number here will divide M. Okay, divide the M that's not divisible by P. And then at the same time, this X here is congruent to one more P. Very funny, huh? Kind of funny. I don't know how to comment on this theorem. But then it is this theorem that told you that how those special group with special order behave. Yeah. I don't know how to comment this. But then do you know what they use? It's also actually they use conjugate action. They use in this proof they use conjugate action on the set of Sylow P subgroup. Okay. And then what they use counting formula. Yeah, the formula, and then what other they use? In that's it, and then they use Sylow theorem also. Yeah. This proof is to use conjugate action on Sylow P set of Sylow P. Okay, but very, very, yeah. I don't know how to appreciate it. Okay. If you found out, you can let me. Yeah. So just now previously you might ask, right, what does the M can do, right? Actually, this M is divisible by the number of Sylow P subgroup. And then it turns out that we know a bit more. That is, this X is actually one more P. How far is it from P? It is one more P. Not very far. Yeah. If you're interested, you should look at the proof. It's also using this action and then stabilizer stuff. Okay. Maybe you mentioned about some result. I think we mentioned it before. Let's see if we want to prove it or not. Or any line you are interested. Do you think so? I think these prove kind of long. not very hard, but then okay, let's not try to prove them. I'll let you read yourself. But then these are, I think these are listed from Artin. Okay, I listed this result from Artin, and then there are also examples in chapter 0 algebra. Yeah, there are others example there you can look at. But these are the one that I found from Artin. Okay. I think we briefly talked about this right last time when I briefed you what we're gonna do. Do you remember? No, can't remember. For example, every group of order 15 is cyclic. Okay, so you might think that why is it cyclic? Why not product cyclic group? So it's impossible. For example, you might think, oh, can I use the order 3 times the order 5 cyclic group to make order 15? But turns out that there's no such group like that. Can I quickly show you why? Cannot quickly. You just need to use the Sylow, third Sylow theorem. Oh, yeah, okay. Yeah, sure. So it is isomorphic to C3 times C5, but turns out that that one is also a cyclic group. Yeah. Okay, yeah, that's right. Turns out that C3 cross C5 is still a cyclic group. So, yeah, then, yeah, right. Okay. But because the order is prime, so it's isomorphic to a cyclic group. If C2 cross C6, then that's the different story already. C2 cross C6 shouldn't be a cyclic group, right? It shouldn't be. For example, C2 cross C4, it shouldn't be a cyclic group. You should prove that there's no order 8 element there. For example, like C3 cross C5 can because you can find a C15 order. Which one is the order 15 element in C3 cross C5? What's the element in C3 cross C5 that has order 15? 1, no? You can try. You go plus 1, plus 15 times only you get back to uh, 0. It's an LCM of the order of the twin. So, okay. Any questions so far? No question. Okay. Yeah, I already posted out your assignment 1. There's 2 weeks, so you can find any reference you want, but then try to cite them. Yeah. 是吗？不会，不会。Yeah. 不是懒。Okay. I can use any reference you want, but then if you need any hints, you can let me know. Yes. Both can. Both can. Yeah. You can link text, you can, but don't use word. Don't use word. Use link text. Link text or handwritten. Yeah. 他们会用的。Yeah, okay, shall we take a break? Let's wait until 3:15, around 3:15. 我比较惊奇的是那个 MA1 的班很喜欢用 latex。好，
有吗？把头里
有，他们讲话是一边讲一边打 latex 出来。那天那个奇安不是这样吗？他没有那个板，他直接打那个 latex。我觉得是被影响他们班，被他影响啊。奇
你觉得比如几个那个多力这样子，
你的功力什么意思？
我不觉得他们打的
哦，没有讲他们打的 skill 啦，我是说来他们的影响力很大。因为你们打的话，比如说ratio 啊，像 ratio 就自己一个人打，你看他周围不会打。
打，
确实，
跟他讲，
确实，
他自己要看电脑的话，
确实，确实，确实。
那个是，哎，那应该是啊，你弄个什么？
什么 class？哦，去要印东西，我忘记了。没有打球今天。
哎，我在打情况，
去哪里打球？哦，是诶，你们哦，对，可以诶。哎，
哦，厉害一点。太难了，
就是我同样说，他整个考虑方面非常，那个程序啊，因为说那个习惯题，那个事情这个叫做如果有
可是那边不是每次都有人打诶，
有
住的人，
那你能
住的人，就是说，
那你的你要用要不
好像要 booking 啊，以前我们直接去了。
本来就，
是
但是不好啊，没有人可以抢啊，一个是的，
这样好，
一个本。
这样。Okay, let's continue. Okay, let's continue. There's one more, I think, a very important result in group theory that can generalize to modules theory, for example, and that we didn't really have a chance to talk about in abstract algebra 1 because there are too many things to do there. I mean, doing details. Which is about a composition series and solvability. This concept here is very important for module and it's also very important for the algebra. Okay, so what's the idea here? So well, we consider a series. Okay, so the series is a bit different from the analysis series. It's not the big sum, infinite sum. Well, this series here is kind of a sequence. Okay, sequence of subgroups, obviously. But then this series here will form a decreasing sequence. So what can you imagine a decreasing sequence of sub? Well, it's like a 俄罗斯套 you know, the Russian dough. The Russian dough. Okay, so you start with your big dough, and then you look at the subgroup inside it, and then inside the subgroup you can dig out more subgroup, and then forever you dig it out. I mean, it will stop, right? For example, it should stop somewhere, right? Where it should stop? Yeah, it should stop with identity verify the element. Okay. Well, we could define the length of a series. Okay. Fix a series. We can talk about the length. Is the what do you think? What do you think is the number of what? I cannot just take inclusion, right? Otherwise, you will play cheat there, right? You just equal forever, then that will become infinite series every time. So we will just care about strict inclusion. Okay, strict inclusion. Okay, otherwise you can put as many subgroup, the same subgroup as you like. Okay, so I think the series here we also consider the strict one. Good. Otherwise, no meaning. Fun. Okay, a series is normal. Okay, it's normal. What do you think? If GI plus 1 is normal in GI. Again, note that this is just normal in GI, not in G. Okay, so there's a subtlety here. You just need to be normal in the previous. That's it. Maybe you can try and see if you can find a subgroup that's normal in GI plus not in G. One question, okay, maybe I give you one question like that. Maybe two questions you can think about it. So first question is, if GI plus 1 normal, we have notation for normal. 三角形 right? So 那个角反了。这个是 subgroup 嘛？ Then like this. 反咩？小 okay, this one is okay. So this one, if it's a normal subgroup of GI, does it imply that GI plus 1 is normal in G? This is a question. Second is, if you know GI plus 1 is normal in GI for OI, does this imply that GI GI is normal in G? So this one is for some I. I'll try to think about this too. Yes. Okay. And then we will denote the maximum length. So maximum length of a normal series. Okay, so we only define it for normal series. G by LG. Okay, if it is finite. We just care about the series of normals. Well, there's a reason to do that. Okay, so let's comment a bit on this LG here. So note that LG is 0 if and only if G is trivial. If G is trivial, I think LG is 0 because trivial group is normal. But then if LG is equal to 0, I think it's if only, right? LG is equal to 0, meaning there's no more normal subgroup. There's no more normal subgroup, but then the trivial subgroup must be a normal subgroup, right? So it should be the trivial group. I think this one is kind of trivial. The other thing is if LG goes to 1, if and only if G is simple. Why? Hey, did anyone introduce simple group here? No, none of you. Okay. In my previous note, I think I have it, but I think no one discussed this yet. But what is G is simple? Anyone can recall? Maybe you can search it up. Non-trivial. If G has no non-trivial proper subgroup. Okay, so you can see that actually it matches up with this normal series counting here. And there's no non-trivial proper subgroup. Okay, because or you take LG equals to 1 as a definition also doesn't matter. Because for a simple group, okay, the only maximum normal series is just G containing E. The trivial group. Non-trivial? Huh? We do not consider the trivial as a simple group. Oh, okay.
Just like we not consider one.
Okay. Yeah. You should think of these things as a prime. You should think of the thing inside this series as prime. Yeah. Exactly how you should think about this simple. I mean, yeah, simple or normal. Okay. Maybe later on. Let me see. Okay. Maybe let me give this definition first. I want to comment about the relation between prime and number, and then this composition series and a group. Okay. So then we will define a composition series, okay, for a group. G is actually a normal series, okay, or the normal series or something like this. Such that there's an additional things, such that the quotient of GI, quotient GI plus 1, so the smaller subgroup, are actually simple. So meaning after you take normal, this G1 is normal in G, right? And then if you quotient out by another normal subgroup over G1, then there's no more normal subgroup inside there. Because GI over GI plus 1 are already simple. So meaning inside this quotient here, there's no more non-trivial wait, I haven't finished, right? This one is a normal, right? I think there's one more adjective I forget. Non-trivial, proper, normal subgroup. 真的咩？这次我发现了。Okay. Okay. Does that make sense? Okay. So meaning there's no more like the normal subgroup squeeze in between these inclusion. Okay, so you should think of these GI as a prime inside your group. This simple, or rather, you should think of this factor as a simple, like a prime factor. Then because give you one composition series, right? You can work out yeah. So n of the portion here, simple portion.
Types of composition series have the same length.
Yeah, right. So this is a very important result. Okay, think of if you have two composition series, should they have the same length? Okay, yeah. Okay, well, so this is exactly the very important result here, which is a Jordan-Holder result. Sorry, yeah, they are very important. This result even hold until like category theory. Yeah. Holder. Hey, I'm not sure it's the same holder or not. I'm not sure it's the same holder inequality. So if you have two composition series, right? Okay, so let's say up to Gn here. And then the other one you have up to Gm. The two composition series. First thing we can prove is that two numbers have to be the same. Okay, so it turns out that being the simple quotient, right? Having the simple quotient is kind of a unique property. It doesn't say that G0, G1, okay, G0 definitely have to be equal to G0 prime because they start with G. But then it doesn't say that G1 have to be equal to G1 prime. It doesn't say. It says that the number of these that give you simple quotient have to be the same. And the list, the hi equals to gi, right? Over gi plus 1, and let's say hi prime that is equal to gi prime over gi prime gi plus y prime. Okay, they should be isomorphic. It could be up to order, up to permutation. Sorry. Can you imagine what happens here? Okay lah. Yeah. It's a good practice. Okay, so it could be isomorphic, but then up to permutation also. So meaning what? The simple factor, right, can appear. Okay, must appear inside the composition series, but maybe in a different order. Because you could imagine that this G1 and G1, Gi and Gi prime could be different as well. As long as they give you the simple quotient. Does that make sense? You can think of some examples that you can do that. Well, I mean, like, so just take some small examples. Maybe take C6. Okay, can you like figure out some C3 or C2, right? I think this is it. They are very normal because they are abelian. And then what is C6 over C3? C2 lah. It's almost like 65 by 2 lah, but then you need to give me the isomorphism. But the moral of the story is like divisibility in integer. And then C3 over E is just C3. But then on the other hand, C6 over C2, C3, and then C2 over E is C2. Okay, so you can see that the length is always the same, but the simple quotient could commute. Make sense? Does that make sense? Yeah. Okay. So you need to prove it for general and not for cyclic group only. Okay, you need to prove it for general. How on earth we're going to do that? What time is it? 3:30. This proof actually is kind of important proof because this technique could be applied to result of similar sort. Okay, that you prove that two numbers have to be the same, and then using some decomposition and stuff. I think I wanted to do this. Let me see what else I need to do before I decide. Okay, I think let's do it. Okay, let's spend our time doing this, and the other should follow very similarly. Okay, let's do this. Okay, how should you start? Maybe you tell me how should we start. How should we start? So you should start with one composition series, right? Okay. And then argue by induction on n. Okay. So if your n is just 0, then on both you only have one way to write it down. So it is the same. Because if n is 0, then that means this g is trivial, like what we remarked just now. The length is 0. There's nothing to do. So suppose your n is greater than 0, okay, then you have another way of writing it. Okay. Suppose n is greater than 0, then you have another way of writing it. So we know that G0 and G0 prime is the same, right? So if these two are the same, then we are done using inductive hypothesis. So suppose that G1 is not equal to G1 prime. Okay. So it's like this case here. Okay, suppose the next one is not the same. So for the next continuous one, is it the same or not? But in this case, we know it's the same. Why? Because in C3, we cannot find normal subgroup, normal proper subgroup only. And then from this case, also, we cannot find not non-trivial subgroup anymore. Don't talk about normal yet. Normal subgroup for you, normal non-trivial one. Okay, but then how does this hold in general? Okay, so we need to do that. Okay, can I skip all the thing that we said just now? So here set up properly. And let me do a bit sloppy in this class. I have a notes. Okay, so suppose G1. Okay, suppose G1 is not equal to G2. Okay, the next one is not equal. Okay, so what should we do here? Well, something to note here is G1 times G1 prime should be everything. Does this make sense? Huh? Set out your inductive proof properly. Yeah, so let's consider G1 that's not equal to G1. Yeah, in this class, I try to not write everything word by word. Yeah. Try to not write everything word by word. You should figure out what I'm talking about. And not that G1 times G1 prime should be G. Why? Actually, not quite trivial here. It's not very trivial here. Well, because we know that G1 times G1 prime should be normal in G. Why is it normal? Do we know that two normal subgroup multiply of two normal subgroup is still normal? This is a bit like the code setting, right? The AB, huh? Yeah. So I'm going to show you now. First thing is you know that they are normal. You know why they are normal? Not that G1 and G1 prime both normal. N greater than 0 case. N greater than 0 case. G1 and G1 prime, why is it normal? Product of two normal subgroup is a normal subgroup. Okay, is it true that product of subgroup is a subgroup? Yeah, man. No, right? So okay, maybe should we like try something? I mean, okay.
G1 G and G plus L, G1 prime G inverse is equals to G1 prime G inverse.
Okay, sorry. So G1 prime, and then let's say G1 bar lah. G1 bar prime, then equals to what? I mean, you want to show group, right? You want to show closure, right? But do they commute? They don't commute.
左边加个 G，右边加个 G inverse，中间加个 G inverse。
Hey, hello, you back? G, you mean how 中间 where's the 中间 here? No, impossible. So what do you mean? Oh, you mean like this, maybe? Like this? Huh? Like that? No quite sure, huh? What? Any suggestion? Oh, I think you want to make it look something like product of things in G1, right? And then G1. Okay, to show normal, I think is what you say lah. To show normal is just put this one and then show it in G. But subgroup, do you know? What is a subgroup? Oh, I think this is the proposition of the product groups, right? Similar. Very similar. Okay, I think it's an exercise, very good exercise. I think you should do it. So please refer. So exercise, refer to the product group proposition. Okay, I think we did this in class last time. Not this class, but the undergrad class. I think we also spent a lot of time doing that calculation. Okay, because in the product group proposition, you only require one of them to be normal, but in this case, you have both. Should be easier. Okay. So, right. Okay. So we know that this is a normal subgroup, and at the same time, G1 definitely is a subset or subgroup of G1 times G1 prime. But there are no proper normal subgroup in between G1 and G, okay? Because G mod G1 is simple. Okay, so this is a bit like a maximal ideal. Okay, so G1 is the maximal ideal, then if you have a larger ideal, it should be the whole ring. So this is a big idea like that. If not, you should try for this. So meaning if there is a normal subgroup in between G1 and G, then G over G1 will contain that normal subgroup. So meaning that normal subgroup mod out by GI is still normal. You believe it? I think it's not hard to prove, not hard to see it. You get what I say? So if you have a normal subgroup between, so let me write down. So if I have a normal subgroup in between G1 and G, then N over Gi should be normal in G mod Gi. Okay, if N is normal in G, then this will happen. Should be not hard to see, eh? We know how to see here. If N is normal in G, then N over Goi. Yeah, the way you make it normal here is just that this becomes the representative. Here is like G and G inverse, right? Here is G representative and G inverse representative. Yeah, maybe you can try and show this. Okay, what time? 3:41. Okay, good. Well, very good. So up to here, what do we know? We know that the product of G1 and G1 prime G. Okay, and if you multiply these two together, we get G. The reason why we didn't write it as a product group is because G1 and G1 prime, the intersection might not just be trivial. Okay, so we didn't put it's not isomorphic as a product. Okay. Right. Next, let K to be G1 intersection G1 prime. So we look at the intersection now. This might not be trivial. We look at the intersection. Well, we also get a composition series here. Okay, do you have any idea how I get composition series here? Do you have any idea? How do I get this Ki? Any idea? You know how I get this Ki? Well, how I do this is I just take a Gi intersect with K. Okay, so meaning I take the composition series of G and then I build a composition series of K. I think intersection between normal subgroup is still normal, right? Yeah, and then you take a intersection between normal subgroup is still normal. Then you need to check the simple part. No? Okay, you need to check the simple part. When you take quotient, is it still simple? Well, possibly you will get repetition here. So we will remove repetition if it is necessary. I mean, it is necessary, but if there's a repetition happen, we just throw it away. So meaning, if I do this construction, intersection, maybe it could be the case that you get repetition. So actually, the hard part to check is what I told you just now. Check the quotient is simple. Okay, so in this case, what's the quotient here? So you need to check that GI intersect n over GI plus 1 intersect n is simple. Okay, so how are we going to check this? Well, there's a claim here. So here's the claim. The claim is this quotient here either is trivial. Okay, if it is trivial, that means they're the same. So the repetition happens. Right? Either it's trivial or actually it's just GI over GI plus 1. A bit like the second isomorphism theorem. Yeah. 为什么是 K 变成非常好的问题？我在做。Okay, I think it's K. Eh? What's the N here doing? I think it's K. It's K. It's K. Sometimes I change the textbook notation, but then I forgot to change it here. Okay. Well, good. So how do we show this? So how do we show this? Well, so let's prove this claim here. So let's look at this homomorphism. So consider the homomorphism GI intersect N. Okay, there's an inclusion into GI. This one makes sense. Sorry. Okay. Okay, please pardon me if I write N again. Okay, so there's an inclusion into GI. And at the same time, there's a surjection into GI over GI plus 1. Right, so now, okay. Well, I mean, to show this, what do you need to show? You need to show that if this is isomorphic, that means this should be the kernel of this homomorphism. Well, but then clearly, clearly what? Clearly, okay, maybe you can show here. Clearly, the kernel of this map should be GI plus 1 instead. Okay, why? Why? Your image is GI modding out by GI plus 1. But then here you start with GI intersect K. So anything that sends to 0 is what? It has to be in K as well. In K, right? It has to be in K. Sorry. First of all, it has to be. Well, how should I say it? Your element is in K and also in GI, and then you send everything that's in GI plus 1, which is in GI, you go to 0, and then everything's in K. If it's in GI plus 1, also get to 0. So if they're both of them, why do you need the intersection between these? Because the thing that you consider in GI also come from K. Okay. Yeah. So the element here must come from both places. Okay. So if you're gonna quotient by GI plus 1, you also have to make sure that the elements come from K. Otherwise, that's not the thing that you do. I mean, you can try and write it out. I'm just telling you why it is to be true. Okay. Cool. The first case is easy, right? First case, this case is easy because this is GI. This is K equals to GI. This is when this is true. Okay, otherwise you have this condition. What do we need to show? Simple. Oh, okay. Okay. Do we have isomorphism directly? I think we should have, right? We should have an isomorphism, right? Oh, wait, let me think. So the kernel here, okay, I think I play a bit cheat here. Okay, never mind. Okay, the book, I think the book is going through here first, and then he go through here, I think. But then now I just straight away tell you the composite, like all the way from here to here. Okay. Okay, so far, so good. Yeah. I think the book they talk about here first, and then they explain about here. Yeah, but then I straight away go straight. It's okay. Yeah. Which one? Which one? This one. Yeah, yeah, yeah. First isomorphism theorem. We have a surjection, ma. Then as long as I found the kernel, then I will have an isomorphism. Right? Yeah. So the thing I need to show actually is the kernel of this phi is equal to GI plus 1 intersect. This is what I need to argue. I think in the book they do this triangle first and then they do this triangle. Why the composition is surjective? As long as the last one is surjective, it's surjective already. Okay, so I think I should write down this lemma. So lemma is the
No, I think it's
ah.
I think it's a completely subjective.
Let me think.
讲它的最后一个死的这个
So 有什么？我给我想想，给我想想，给我想想。对，因为 like if this is not subjective, I cannot pull it back. But turns out that this is an injection. Yeah. But then this injection is okay lah. So I mean, wait, let me think what you are trying to say. So if it's subjective, yeah, pull it back. Oh, might not be true. Might be true. Okay, no wonder the book need to go through the GI first. Crazy. Oh, they might not be true. Okay, I think you are right. Okay, so you know what happens here? Because you might subject to something that's not in here. Yeah. Yeah, right. Okay, good, very good. No wonder the book had to pass through there. Okay, so okay, no choice. Then we need to stop here first. Very sad. We have to go through here first. We have to go through here first. Okay, too sad. Okay, then we have to go through here first. So we only stop here. Then what about this guy? How about this guy? Can we compare these things? How do we compare these things? Okay, so well, I mean like so GI intersect K is injective to GI, right? But then you quotient on both sides, you should retain your inclusion. You should retain your inclusion. This one okay, I think. Okay, you quotient now by the same thing. Okay, Then what did you see here? You should just see this quotient as a subgroup of this guy. That's it. For now. And then this subgroup is normal. Okay, so this subgroup is normal. At the same time, this is normal because what? Because K is normal in G. This is enough. And excuse me. I over GI plus 1 is simple. GI over GI. So what are we claiming here? Oh, okay. So maybe this one's up first. Okay. So this is normal. Okay, because K is normal. And then from this is simple, what does it say? Since this quotient is simple, and then you found a normal subgroup that is inside a inside a simple group. What does it mean here? If this is not trivial, this must be the big group, the original group. Be the GI. Okay, does it make sense? Okay, so yeah, so this is a normal subgroup, and then since this quotient is a simple group, you found a normal subgroup, but simple group says what? There's no proper simple subgroup, right? So it has to be the group itself. It cannot be trivial. If it's trivial, that's the other case. When this quotient is the same. So we suppose it is not trivial first. Okay, we suppose it's not trivial, then it has to be the big group, the original group. Okay. 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 Then how do we infer back? How do we infer back here? So what we did was, so therefore, we actually have two new composition series. So one we have G1, one we have G1 prime. Okay. And then both of them you should continue with K. Okay, both of them you should continue with K. And then by inductive hypothesis, the composition of K should be the same. Do I use K or NK? Okay. So it's now left to check whether G1 over K and G1 prime over K is the same. Okay. So how do we build this up? So G1 over K is just G1 over G1 intersect G1 prime. But then this is isomorphic to G1 prime over G1 prime. So this is, I think, second isomorphism theorem. Okay, and then you can do the same game to push it back to G over G1. And then you should show this isomorphic to G1. Okay. Okay. Okay, does it make sense? So what we did was if we have two composition series, right, that differ at the second spot here, what we prove here is what happens is the rest should be the same. Common. Does this make sense? Any question? Maybe any question so far? No question. Does this make sense? I think so far our length is quite short, huh? We didn't really see this happening here because we kind of stopped here. Maybe you could try with a longer, a larger group. C12. Yeah, maybe you can try C12. Yeah, try, okay, maybe let's try C12. Is it long enough? So try 5. You try and work out it already. So try C12 with different G1 and G1. Yeah. Okay, sure. Yes. When's our first replacement class? Let me check. Because I just got my room today. So I haven't really checked. I fix it at May 6th. May 6th. Okay. See you. Next Wednesday. Okay.
对啊，iPad
是卡的吗？